this. All right, so where are we at? We are in 7C. So what have we done so far? We did 7A and 7B. So in 7A, quick recap, we introduced probabilities. So that was a big thing in 7A. So we did theoretical probabilities. We did relative frequency. They're both kind of figured out kind of the similar way. We take how many times the event occurs over the total possible number of outcomes. And so whether we're doing theoretical probability where we're predicting stuff and we're making assumptions, like a flip of a die is equally likely, a flip of a coin is equally likely. And we're making predictions about things that are going to happen. The other way was relative frequency. That's where we're looking back on things. 668 198. We're looking back on things and creating a probability for that. And then 7B is when we started introducing ands and ors. So if we have an and probability, so we talked about this last time, but the probability that I get like one head is going to be a half. You might figure out the probability of getting two heads is going to be less than a half. It's going to be more rare. And we can enumerate like all those different combinations of what heads, tails, tails, heads, right? Tails, tails. And you might figure out it is 1 out of 4 times that's going to happen. And so if we think about this, maybe 2 wasn't a good number to use. But the way that we got this and the way that we figured it out is basically we're multiplying things. And so if we have 2 heads, it's going to be 1 and 4. If we have 3 heads, there's 8 options. That's going to be 1 in those 8 options. Ooh. So that was and probabilities. So and probabilities, this is if they were independent. The other thing we had in and probabilities was like the M&M example. So if we're going to eat, I think it was like 10 red M&Ms out of 30 total M&Ms. We're going to pick one out and eat it. So this is the without replacement. So when you do drawings without replacement is what they call it. That's, I guess, the technical name you'll probably hear it under. It is be a drawing without a replacement. They're not independent. They're dependent on each other. So what happens is we end up going down. So if we had eating red M&Ms, we would have to go down 1 each time we ate a red M&M. They didn't ask you, but it is something that I guess could be asked. If we start out with 10 red, 10 blue, and 10 yellow, I think was the example. If we pull out a red, if they want a red and a yellow, right, you'd also have to consider, I guess, that. So if it went down 1 because you ate the M&M, but you would still have 10 yellows. So it depends what they're asking. I don't think we had any examples like that where they asked different colors, but they could ask that. I think we all asked the same color or something like that. Or they were all aces or something like that, right? What else? Or probabilities. That was the other thing. So we did and probabilities. We did or probabilities. What do I say? When we do or probabilities, this is kind of going back to the stuff with the logic. We are adding stuff together. We're adding sets together when we talk about or. Sip of coffee and think about that. There was, I don't know, if you want to roll a 3 or a 4 on a dice, something like that, there's probably a 1 in 6 probability this thing's going to happen. There's a 1 in 6 probability this thing's going to happen. And so if I want to think about rolling the side of either 3 or 4, or 4, I'll expand this so it didn't do that wraparound. This is going to look something like what? 1 6 plus 1 6. So if you're talking about two sides of the dice, you're talking about a third of the dice is what you're talking about. So when we talk about OR probabilities, I think we did it with drawing cards. That's what it was. 2 kings, right? We had the 2 kings, drawing kings or drawing red kings or black aces, I think is what it was, right? And so drawing, let me do some text here. Drawing what a black ace is 2 out of 52, I think. And then drawing a red king was 2 out of 52. And so I think what we're going to end up getting is 4 out of 52. We're doing that. We would get something like 4 out of 52 if we added those things together. And so this is if your sets are disjoint. The other thing we had, and imagine my cards are here, is if your sets are overlapping. So we talked about like maybe if we look at the set of diamonds and we look at the card number 5. So if this is a horribly drawn diamond over here, and this is like the number 5 here, there are, I believe, 13 cards in this suit. There are 4 cards here. So if you told me 17, you'd be off by 1, and you'd be off by 1 because there's this thing called the 5 of diamonds right in here that is overlapped. So you have to consider whether the sets that they're talking about are overlapping. If they are, we have to subtract the overlap. So that was what we talked about last time. Today we need to get into the law of large numbers. Are there any questions over all that stuff? I know I just blew through it. But are there any questions over the stuff that we have done so far, finding probability? All right. So the law of large numbers, what does it say? What does it do? If we average this side on a dice, we add up 1, 2, 3, 4, 5, 6 and divide by 6, you might figure out we're going to get the number 3.5. And so theoretically, we should be rolling an average of 3.5. And so the law of large numbers, oh man, I really thought I grabbed something with the coin flip and probability, but I think I messed up maybe a little bit. But this is the same concept here. If this is our theoretical probability, the more trials that we do, the closer it should get to our theoretical probability. So if you did coin flips with heads or tails, this would be 0 to 1. The theoretical probability would be 1/2 right in the middle. And so, well, I guess we'll just jump into it because this is the first question. Yeah, exit out of that. So at first it might be off, but the law of large numbers says that as we do more trials, it should be getting closer and closer. So what are they saying? Explain the law of large numbers. Does this law say anything about what will happen in a single observation or experiment? Why or why not? So what does it say about single experiments? Spend as long as the homework as it takes to get through the homework. Trials independent and want to have, yeah. And so if you're doing independent trials, they're all going to have the same probability. become proportional. But does the law say anything about that? Well, what if I get to run ahead? What does it say on if I'm doing what 3, 6, 9? What is that? 10, 11. If this is my 12th trial. What is the probability of the heads going to be on the 12th trial?
Would it be a half?
Yeah, it's still going to be a half. It's never going to change, right? And so we're going to get into this later, but like one of the things that the law of large numbers kind of says is that in the short term, runs can happen, right? There's this sort of thing, this loaded word here, large. What does large mean? And I think another question comes up is like, well, how many trials do we need before like this thing starts getting close? Well, it depends how much accuracy you need, because the further you go, technically, the closer it should get if it's following the law of large numbers. So here we can be very far off. Like you flip a coin once. Let's go through that. That's what I did with the other class. Let's like think about like maybe a series of coin flips. So if I do like one coin flip, the probability of heads, right? Theoretical probability of heads is the thing that we should be approaching with the law of large numbers. But in reality, when we start flipping things don't just like come up automatically 50%, right? When we actually flip it and do the relative frequency, if I do one trial, that's what I said, or one flip, my probability of heads here, if I get one heads, it's going to be 1. If I get two heads, even after 2 trials, now my probability of heads is looking like what? It's still 1. Okay, but maybe the 3rd time I get tails. And so this is hopefully like what I hope you have kind of pictured in your head, is that we just keep flipping this thing over and over again. And I keep looking at the probability of my heads. And now the probability of my heads is 2 and 3, or like 0.66 repeating. And then maybe I get another heads again. So now my probability of heads is what? 0. What is it? 3 and 4, 7.5. It could go up a little bit. It could go a little bit further away from my expected probability, my theoretical probability, right? In the short term, it could go further away even. But the theory is that the more that we do, and let's say we get another tails or something, the more that we do, it should get closer. And how many more do we need to do? Depends how close you need to get. But we need a large number, and they don't really say. Large is kind of a loaded word, I feel like, right? We got what? Doing math. 0.6. I think we're back at 0.6. And so the more that we do, we should be getting closer and closer to 0.5. It will probably never, it might be exactly 0.5, but it'll probably never hit that. Like in most scenarios, it will get like probably very, very close, like 0.4999, right? Or something like that. Or maybe 0.501 or something. But it's going to kind of bounce around there. It's going to bounce around 0.5 as we get really large. And so what does it say about what will happen in a single observation? So single observations, anything can kind of happen. We can get heads or tails. It's going to be 50% heads or tails either way. So it doesn't say anything about what sort of happens in any single observation, other than if they're independent trials, then they're going to be the same probability over and over again. But we can get runs at tails, right? We can get tails, 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 tails. And the probability of the next one, ooh, what happened? Where did I go? I clicked off. Shoot. What happened? What button did I click? Well, my history. Did I like click a new window? Y'all see the window still for quizzes? There it is. What the heck happened? Weird. Now I don't even see that window that was there. Oh, that's a different window. It's a security browser. That's stupid. Okay, I thought I was doing annotations and it did something weird. Sorry. But the law of large numbers says nothing about runs in the short term. And we're going to get to a lot of examples that basically kind of go over that sort of the same concept. It goes into the gambler's fallacy. When you think you have a hot hand or whatever that is. The law of large numbers, so this is pretty much just out of the book. What I would do, I wouldn't read like this crazy math speak, right? Consider an event, so consider getting heads. What the probability of getting heads in a single trial is, what, a half? So you're getting heads, its probability is a half. The law of large numbers says that for a large number of trials, and again, I feel like this is a kind of a loaded word. What does large mean, right? How many do we need? Again, that's something that that's something that gets studied in statistics. It's like, how many do we need for this sort of accuracy? Because short answer is like trials are money, right? If you're conducting trials to test something, that's money that you're spending. And so we want as little trials with as much accuracy as possible. So that's something that gets studied quite a bit. How many trials do we need, and how much accuracy is it going to give us? And are we doing hand grenades, or are we doing heart surgery? Like, what are we doing? How much accuracy do we need? The proportion for a large number of trials, the proportion in which an event A, so the event of getting what heads, will be close to 1/2. So if we do a lot of trials, the observed probability or the relative frequency should be getting close to the theoretical probability. The larger the number of trials, the closer it should get to that 1/2. And individual trials always have that same probability of 1/2. So I talked a little bit about it. Like if we get a run of heads, people always think like you're going to get a run of tails at some point. But in the short term, maybe not, right? It could be like maybe two more heads there and then two more tails there. It catches up, but it catches up when we're talking about a lot of numbers, right? And so you may not get those runs of tails like you get the runs of heads. It might only be slightly more here and there. And so it happens over a very, very long span. So I guess the fallacy in that is believing that like in the short term that things are going to balance out, and they don't. There's no guarantee of that in the short term. And so that's essentially what the gambler's fallacy is. Okay, so what is expected value and how is it computed? Should we always expect to get the expected value? Why or why not? Y'all don't have to type this stuff in if y'all just want to talk about it. Like if we just talk about this. I feel like it'd be quicker, but if y'all want to type stuff in, I guess it's fine too. So what is the expected value? Sorry.
Is it like the average amount like you expect to gain, or
That's the best definition I've heard. Yeah, I was about to give you a really smart ass definition. It's the value that you expect. What is expected value? No. But it kind of is, right? It's the value that you expect to get each term on average, right? And so we know that we could make what, 70, let's just do 70 and 80, right? Well, yeah, let's do 70 and 100. So that when we average them, it's 170. I can do math quick. 85 average, right? And so we know if it's an average of 85, that doesn't really tell us what we did individually on the individual test. So the individual trials can vary quite greatly from a C to an A plus, right? But our average is going to be like an 85 or something like that. So when we think about averages, it doesn't really tell us what we did individually here. And so should you always expect to get the expected value on the individual trial? That goes back to like the individual grade, right? It doesn't really tell you what you're doing on the individual trial. So goes back to the casino, right? I could make $1 million here, but guess what? I'm gonna lose $1 here. I'm gonna lose $1 here. I'm gonna lose $2 here in the casino, and eventually all this money that I'm losing is gonna catch up to me, right? I'm gonna end up losing more money than I'm gaining at a casino. So individually, you could bank, or you could go like really into debt individually, right? On any individual trial, but it's not going to tell you like the overall. You're probably losing $1 or something each time you play a game or something, right? There's a very probably low expected value overall. But individually, you could hit the jackpot. You could lose your bankroll. I don't know. Getting foolish, betting it all. Are there questions over this? Do you think y'all are getting this down? This is a very, very weird sort of thing. And it like there are some like counterintuitive elements, right? Because I think and casinos know this. They know this is our intuition, right? We get a run of heads. Oh man, so bad. Do I want that thing to be tails next, right? But guess what? The probability of tails on the next trial is still just a half. That coin, each flip is independent. So it is very like there's something very counterintuitive happening here. I feel like, and it's really weird because individually we expect this thing to catch up and for it to approach the theoretical probability, but in the short term, we don't get that. Runs can happen. It's runs are a fact of life. That's why they made Pepto-Bismol. Question. No, are we getting this? I'm going to proceed then. I think I got another slide on this anyway. Come on. Consider the 2 events. So they say consider 2 events, and then right after they say it could be more. So they're going to start with 2 events, and this is the way that we find it. We multiply the value of the event times the probability of the event. Each has its own specific value. They are some of those 2 events. Formula can be extended to any number of events by including more terms in the sum. So I think that's pretty much copy and pasted from the book. This is what I added. So on average, right, this is a sort of average amount. This is the amount that you can expect to gain or lose for each turn, each policy you sell, each event that's happening, right? Each coin flip. Each poker hand. Full question view. What does it say? This is a weird one. Decide whether each of the following statements makes sense or is clearly true or does not make sense is clearly false. Explain your reasoning. Excuse me. If you toss a coin 4 times, is it more likely to land in heads, tails, or heads, heads? Did I skip one? I think I skipped a slide. I did. Oh, man. All right, let's jump back. Sorry. This one, I think, comes before that. We'll get back to that one. So does this make sense? This is basically the same question. The expected value to me of each raffle ticket I purchased is a negative 85 cents. I skipped right past this. But it shouldn't, hopefully. So does it make sense that if I go buy a raffle ticket, I'm expecting to, this negative means I'm losing 85 cents. So I'm probably spending $1 on the raffle ticket is what I would guess. And so I'm not going to lose a whole dollar. I'm going to lose a little bit less than $1 because those prizes are going to make this go up a little bit. And so to me, I would say that makes sense. Good deal. See, it took us 3 seconds. And I think the point of that question is that it has a negative expected value. Can you expect to lose money on a raffle ticket? Yeah, probably lose around 85 cents on a $1 raffle ticket, right? Is it wrong device? Is it more likely to land on heads, tails, or heads, heads, heads? It is more likely to land on this than that. Sorry. So they are saying that this is more probable than this one. And this one is one that is confusing as heck, but I will spell it out. I hope some people got this wrong. Just being honest. Yes. Okay. Flip a coin 4 times. These are all the possible outcomes. So one of the things I think people read when they see this is they think this is any combination of 2 heads and 2 tails. But that is not what the question is asking. They are asking for the specific combination of, is it going to be heads first, tails second, heads third, and then tails fourth. So if we're looking here, finding the probability of these, finding nothing but heads is 1 in the 16. And guess what? If we're talking about this specific combination, that's also 1 in 16. So they are talking about the order here, right? So maybe that's another thing that's kind of throwing people off. But they're talking about the order. If we look at what 2 heads, 2 tails, there are a few different ways to get that. So I think that's what some people interpret that to mean. So there's what 6 out of 16 different ways to get a combination of 2 heads and 2 tails. But they're asking for this specific 1 string of heads and tails. And so it's not more likely to land on nothing but heads than or a mixture. They're both equally likely. So all strings are equally likely, basically. And we could extend this, right? We could extend this with 100 flips or something. Okay, understanding the law of large numbers, should you toss a fair coin 10,000 times, should you expect to get 5,000 heads? Why or why not? What does the law of large numbers tell you about the results you are likely to get? So should we expect exactly 5,000 heads? That's the first question.
No.
No, it's not going to be exact, right? What does it tell you about it? It's likely to be what? Close, probably. But it'll probably be a little bit over, a little bit under. What does it tell you? As we flip more times, the ratio of heads should be half, right? It should be getting closer to that half. Are there any questions over this? So it's not going to be exact, right? Reality is not exact when we do things. When we flip a coin, it's not going to exactly come out 1/2 times heads, 1/2 times tails, right off the bat. If we do it enough times, it should average out. But the key word is you have to do it enough times. You have to do large numbers of trials. It's not called the law of small numbers, right? It's the law of large numbers. So we can't make these sorts of predictions in the short term. And it's not going to be exact either. Insurance claims. All right. So now I think we're doing stuff with expected value. Find the expected value. Okay, this is 19. This one, this problem's good. Don't get me wrong, but I don't like the problem. But I do like the problem. But I don't like the solution. Find the expected value to the company per the policy sold. If the company sells 10,000 policies, what is its expected profit or loss? So first, we're just going to find the expected value. So if they are selling, we're finding this from the insurance salesperson. Yes, expected value to the company. So there are basically two different perspectives you can look at expected value from. If you're expecting to lose $5 for every game you play in the casino can expect to gain that $5 that you're going to lose, right? So whether it's positive or negative depends whose perspective you're kind of looking at it from. But here we're doing it from the company, so we have to look. If they sell something for $300, we have to ask ourselves, are they taking this in or are they paying this out? Is basically what we're asking with each of these amounts. So they're selling a policy for $300 based on past data and average of, and now they're going to give us a bunch of probabilities and values. So 1 in 100 policyholders will file a $10,000 claim. 1 in 250 will file a $25,000 claim. And an average of 1 in 500 will file a $50,000 claim. So we talked about expected value, but the expected value is the value of the event. Basically, we're multiplying value times probability, right? Value times probability, and then we're going to add that to value times probability. We're just multiplying value and probabilities, and we're summing them up. And so I'll give you a little bit of a start on this one. So an insurance policy sells for $300. So if they're selling something for $300, that $300 is the value. So then we have to ask ourselves, are they collecting this or are they paying it out? So they are getting this. So it should be positive. It's kind of silly, but we should probably do it. The probability that they're going to get that $300, they are guaranteed. It is 100%. It is a 1 probability, 1.00. The next thing I'm looking at, now I'm looking at all this information they're giving me. They might have to pay out $10,000 is what this is telling me. If someone files a $10,000 claim, they're going to have to pay that out. So it's important to make that negative because they're paying it out. There is a 1 in 100 chance they're going to have to pay that out. Let me extend this so I got enough room. What am I doing next? 25,000. So there is a chance I might have to pay out 25,000. And the chance I might have to pay that out is 1 in 250. And so I think there's one more I have to do. So I got to write something about what this 50K. There's a 1 in 500 chance they might have to pay that out. I'll let you finish that last little tidbit. So there's one more thing to put in there. And if you get a weird answer, I don't know what to tell you. Go with it. Try something though. You're gonna have to do this. Definitely do a few of these on the test. or before the test. There's a few on the homework. Is it? No, okay. My quizzes on the phone was lagging. I think this thing's frozen too. Have we answered it? Oh yeah, okay. It froze. Okay, here we go. Okay, he wrote out some words. I didn't give it to you. It should be 0. Okay, so we have 300, and we have this. I think this was the last thing that I didn't set up. And we get 300 here. This is what? Minus 100, minus 100, minus 100. So 300 minus 300. I don't like this question because it's not realistic. If I wanted to make money on this policy, how would I do it? And maybe it's a stupid question. If I want to make more money, I charge more money. If you charge 301, I think this would make your expected value what? 1? Select. So however much more they're going to charge for that policy, I guess it tells them what the break-even point is on their policy. But in reality, like an insurance company is not going to make an expected value 0. And the other thing I don't like about this is they said, well, if we sell 10,000 policies, how much are we going to make? You're going to make 0 per policy. For 10,000 policies, you're still going to make $0. You're not making anything off your policy. Might be the way insurance is supposed to be run, or morally, but that's not the way it's run. And so, I want to do the second question, which is 20, which is the same question, different numbers. So now they're selling it for $600. We have on past data 150 will file a $5,000 claim. 1 in 100 will do 10,000. 1 in 200 will do 30,000. You know, I don't know if this might save y'all, but it might. We're doing the 600, and that's a 1 probability. You know, if you got like something like minus 5,000, and we're multiplying it by what, 1 over 100? Like this number, drawing this number right here, right? I don't know if it helps you put it in the calculator or something, but we got a minus 5,000 and we're dividing it by 100. If we're multiplying these two things together, I just have a 1 on top. It's just kind of like I'm putting that 5,000 on top. So I don't know if that'll help you throw things in your calculator faster, maybe. I imagine the person that said minus 600 did something to make that first number negative and not the first one. Does it do it in the color that I pick? Okay. No. Maybe.
Oh wait, do we put the money symbol?
Yeah, it should be there. Okay. I think you should get 250, right? That's what I was getting. What was I saying? 250, 250, 250. Woo! You entered too soon. The expected value for one policy is what we're doing. So 600. These, I think, give you minus 100. That last one gives you minus 150. So if we take 600 and we minus 350, we should be getting that 250 per policy. So this is my expected value per policy that I sell. And so then the next question says, if we sell, what, 10,000 policies? Is that what it is? If we sell 10,000 policies, and we're making, what, 250 each policy, how much are we going to make? Three, four. 1, 2, 3, 4. There we go. Oh, you could have done this before we even got to this section. Unit analysis. This is the apples, right? Buy so many apples. At what price? 10,000 policies at a price of 250 per policy. Well, that's what we're making. What is that? It's the same thing you answered last time. You're just ahead. Yep. So we add 4 zeros to 250 is what we're doing. Multiplying by 10,000. Ooh, gambler's fallacy. This is where we're flipping heads. Yeah, it is. We're flipping heads. You're playing a coin toss game. You win $1 if it's heads. You lose $1 if it is tails. There's the first 100 coin tosses. Heads comes up 46 times and tails comes up 54 times. This should take you 3 seconds to answer. What percentage of times has heads come up in the first 100 tosses? And then we're going to answer this later. What is your net gain or loss at this point? But we get it 46 times. What is that percent? If it happens 46 out of 100 times, don't rack your brain too hard with this one. It's happening 46 out of 100 times. It must be lagging because I already submitted. Sorry, but this I should just like skip past this question probably. Ooh. What is your net gain or loss at this point? So here we can figure out, you could probably figure out expected value for one game or something and multiply it by 100 or something crazy. That seems like a lot of work, and I wouldn't do that. If you got heads 46 times and you're going to win $1 for each heads, I believe you won $46. And if you're going to lose $1 each time tails comes up, I believe you lost $54. I think the easier way is just to think about how much you won and lost. And so for quizzes, it's a lot easier to put in negative and positive numbers. So if it's positive, it means it's coming to you. If it's negative, it means you lost it. So positive would be a gain, negative would be a loss. And so if you're going to do a negative, do like negative $sign and then maybe the amount. Okay. So I'm getting 46. I'm losing 54. I should be losing $8. What are y'all telling me? -8. That's right. Yeah, negative needs to come before the $sign. I think maybe the -0.08 is like the expected value per game or something if you did it. But you did 100 games. So you'd have to multiply that by 100 and get the $8. Suppose you toss the coin 200 more times for a total of 300. If I'm being honest, I don't even like the fact that they gave us this. It confused me more than it helped me. But they're tossing it 200 more times. We got a total of 300 tosses. And at this point, heads comes up 47% of the time. Is this increase in percentage of heads consistent with the law of large numbers? So remember, we had 46%. It went up to 47%. Is that consistent with the law of large numbers? Is it happening? Is the thing happening that we think? Or is it doing something else? And so what's the expected probability you're trying to get? 50%. And so if we go from 46 and we do more trials and it gets to 47, that is indeed, it is getting closer, right? It is definitely getting closer to that 50. So it is following the law of large numbers. Now, it's getting closer there. I want to say proportionally, that's the word I'm looking for in my brain. We go from, where's my text? 46% here to 47. But now we want to figure out the net gain or loss at this point. So again, I would figure out how much you won and how much you lost. So you won 47% of the 300 tosses. They don't tell us how much we lost, but guess what? If we won 47%, I'm pretty sure that means we lost 53%. Tails would be the other half of that. And so I think we might have to figure out what 47% of 300 is. We might have to figure out what 53% of 300 is. But this is how much you gained. This would be how much you lost. That seems right. And so I think they're trying to get maybe at something here. We're starting off with 46. 46 is below the 50. We're not doing good, right? We're not doing good in this game. 46 goes up to 47%. Seems like we should be doing better. We got a better probability. What are we doing? But we lost $8. We have a better proportion now, but now we're in the whole $18. So we're actually doing worse off financially overall, right? So proportionally, we got better, but like financially, we still did worse. We're still in the hole. We're in the hole even worse now. But this is where we're getting those numbers from. So the 47% of 300 is what I won. So if you won 141 times and 53% gives me 159 is what I lost. I'm winning this. I'm losing this. So if I do 141 minus 159, I should get a loss of $18 or negative $18. Okay. How many heads would you need in the next 100 tosses in order to break even after 400 tosses? Is this likely to occur? So how many tosses would I need to break even? Out of 400, even Stevens, would it be what, 200 of each? 200 heads, 200 tails? So just a number. Just how many more heads? If we had 141, we need 200. So I believe we're 59 away, right? And so the next question they're asking is if we're going to flip this thing 100 more times. Oh, what are y'all doing? 200 minus 141 is what we did. We had 141 and we needed to get to 200. Oh, what are y'all doing? So they ask, is it likely? And so the book says it's, well, I should ask y'all. Is it likely? I mean, idealistically, like probable wise, right? If it's an equal coin and it would like did things precisely like even, it would be 50, right? At most. And so you're betting on something that's even higher than like that than the average, right? So you're probably not going to get more than 50, right? It's not a good bet. And so is it likely to get 59 heads? The book says it's possible. Like it does happen. It's not like completely unheard of, but it's not likely. It's not something I would necessarily bet on. And so far it hadn't been turning up your way either anyway, right? So there might be start to be some reason maybe to believe that the coin might not be fair at some point. Depends whether it continues following the law of large numbers. Gambler's fallacy coins. Suppose you play a coin. Okay, same thing. Suppose that still behind after 400 tosses, you decide to keep playing because you are due for a winning streak. How does that illustrate the gambler's fallacy? So how does this relate to like the law of large numbers and the gambler's fallacy? Yeah, but like how does that relate? Why is that a thing? Why is it not a thing? That is absolutely not true. So I don't know. That is what the gambler's fallacy is, and it's absolutely not true. You're not due a streak of good luck.
Yeah, I misworded that. I was trying to say
Okay.
that like he believes like after like a certain amount he will, he will win.
Yeah. I kind of figured that's probably like you're probably trying to like explain the gambler's fallacy and what he was believing. I was hoping that's not what you're believing, because that is the gambler's fallacy, right? You're due a streak of good luck. So the thing here is like heads could consistently come out behind, right? It might get close to 50, but maybe it gets 49%, right? But if you're doing 49%, and now you want to do like a million trials, let's just do some crazy number, right? You're going to be even bigger in the hole than you were. I don't even know what it is. 0.49 times a million. 0.49 times 1, 2, 3, 4, 5, 6. And we're going to subtract 0.51 times 1, 2, 3, 4, 5, 6. You're 20K in the hole then. Like, even if it gets better proportionally, the more trials you get, the more in the hole you're going to be, as long as this is below 50. So there's no guarantee that this thing will ever get above 50, even with the law of large numbers, right? This thing could always be in the hole on the head side. It's going to get proportionally closer to that thing. The more trials you get, as we saw in like part A and part B, we went from losing $8 to 18. You're just going to lose more and more money. Like, and this is sort of like the gambler's fallacy. Part of why gambling is addicting. They just use a lot of psychological manipulation in casinos. All the flashing lights and everything. They really like appeal to this like really sort of primordial instinct that's in us. It's like, ooh, flashy lights, and it's like you remember those wins. You remember those wins of like $1 million, right? You're like, oh, I won $1 million, but you like you tend to forget, oh, I spent $20 here or $30 here. And so you should expect to lose money going into a casino, right? And we'll see in an example of blackjack. Blackjack doesn't have that good of odds, really. For it has good odds for the player. Like the house doesn't have a very much of an advantage. But yeah, the gambler's fallacy is that like things are going to turn around. You're making some sort of assumption about runs as well. Runs can happen, and you can have a bad streak. Bad streaks happen, and you can continue to have a bad streak. It tells us nothing about the short term either. So part of the gambler's fallacy is assuming that things are going to balance out in the short term, and we don't get that. It's called the law of large numbers, not the law of small numbers. Sorry. Consider a lottery game in which 6 balls are drawn randomly from a set of balls numbered 1 through 42. So we're doing a lottery with balls. 1 week, the winning combination is 5, 12, 23, 32, 5, 36, 41. The next week, the winning balls are 1, 2, 3, 4, 5, 6. Is the second win set more likely or less likely or just as likely as the first? I feel like this goes back to that heads tails thing. If you want, we can find the probability. Draw of what? Of drawing a 5. What's the probability that we would draw a 5 if we're looking at this first one over here? We got 42 balls. It's going to be something like what? 1 in 42. What's the probability that I'm going to draw the next ball, which is a 12? Ooh. So I'm still talking about a specific ball, a 12, but now I went down to what? 41 balls? And I think it's going to look similar with the next one. If I want to draw a, what, 23, it's still going to be 1 in 40. If I think about what, drawing a 1, guess what? It's still 1 in 42. So my probabilities of drawing these things are going to be the same if I think about how I'm figuring these things out. And so I think they're trying to get something out here because math is all about like finding these patterns, recognizing these patterns. And now that pattern recognition is probably working against you. Just because this thing follows a certain pattern that we're familiar with, right? It doesn't make it any more likely or less likely than like this sort of thing. If we're drawing the same amount of balls from here, we're drawing them at random, everything is equally likely to get chosen. This pattern is no more likely than this pattern. They're all equally likely. Any 6 balls that we pick. Does that make sense? Are there questions about this? So there's something, I don't know, like this is very familiar, right? I feel like it's like that pattern recognition thing. We're familiar with this thing. We're like, oh, that has to be, something has to be happening there for them to produce this pattern. They're doing some trickery or something. I don't know. But they're not. Like it could be, it could be. We could get 1, 2, 3, 4, 5, 6. It's equally as likely to get any other combination. So all combinations, any combination of numbers you can give me should be equally likely. As long as they're like independent, they all have the same probability. I guess those aren't independent, those are dependent. All right, so now we're gonna do the blackjack example. In a large casino, the house wins in blackjack with a probability of 50.7. So that is not a large gap of winning, right? It's like 0.7 over. So I believe the other side of that is probably go ahead and do it. But if they're gonna win 50.7% of the time, I believe it's 49.3% of the time that they're gonna lose. All blackjacks are 1-to-1, meaning if you win, you gain the amount you bet. If you lose the amount you bet. So if we bet $1, we win $1. If we bet $1, we don't get our $1 back. We end up losing the $1. So you basically double what you bet, or you, or you basically give back. You pay for the game. You know, you don't get your money back. And so if you bet $1 in each hand, what is the expected value to you on a single game? This, they round it to 3 decimal places. It is a money amount. 1/10 of a cent, I guess is what they're doing. But it should be an exact amount, I think is why they're doing it. So if I'm winning $1 50.7% of the time, and I lose $1 49.3% of the time, what is the expected value of a single game? Remember, we do value times probability, value times probability. Convert this to a decimal. Don't forget to do that. 0.507, 0.493. If you're losing, it's negative $sign. We're doing it from the player's perspective. So if we bet it, what's the expected value of a single game from the player's perspective? And the second question is house edge. I'll talk about that in the slide. We won't spend too much time. It's the same thing. Other side of it, but it's the same thing. All right, value times probability, right? That's what we're doing. And so if you're the player, I hope you got a negative amount. We're gonna win. We're gonna win $1. I believe what 0.493%. We're going to lose $1. And we're going to lose that $1 every time the casino gets it. I forgot my addition sign up in here. So I believe that's the setup.
Wait, so what decimal place does it go to?
3 decimal places.
Okay, thank you.
And I think gives you what 0.014. And so we should be losing that. Loses annotations. Get out of here. Well, you're telling me you're trying to round stuff. Ooh. So yes. So you got to add back the amount. Actually, I think you did it the other way around. So the player, they're going to get $1 49.3% of the time. They're going to lose $1 50% of the time. If we calculate that, that gives me the negative 0.014. That is the player's perspective. The other thing is the house edge. So the house edge is the casino's perspective. So they're losing $1 the 49% of the time, and then they're winning $1 50% of the time. So it's exactly the same thing, but opposite. We flip the signs on our winnings, basically. It's a negative becomes positive, positive becomes negative. And we get a positive 1 cent and 0.4 of a cent. So the casino's making a little over a penny for each $1 a person plays in blackjack. Is that a lot? Not really, right? But are they going to make money? Yep. They're keeping their lights on for sure. If you played 100 games of blackjack in an evening and you bet $1 in each hand, how much should you expect to win or lose? Explain. Okay. I just need the I want to know how much you're going to win or lose. And so if we're going to lose like this, what? 0.014 per dollar game. How much if we play 100 of those games? So this is for every one game, and we're doing 100 $1 games. Oh man, 100 times that, I think you're going to lose $1.40. So they're not making too much, but they are making some money. Oh, what else are you telling me? That's it. Oh man, you got to put another decimal place in your monies. I don't know why y'all keep doing that, man. I need the nearest cent if I'm talking about money. Okay. And now I think we got something similar. Now we're doing 100 games. But each of those we're betting $5. So we're betting 5 times the amount. Hint, hint. So how much should you expect to win or lose? So I think we're doing this 100 times, and we're betting $5 now. So if it's 5 times the amount, and it's 100 times the amount of games, it is exactly kind of how I'm saying it. Times, right? Okay, so I think we should be losing $7. Is that what y'all got? What are y'all telling me? That's it. -7. 97, -7, 700. Oh, I don't know where that came from. What? Oh, I didn't have put the minus in there. What was that?
Forgot to put the decimal.
Oh, okay. I see. Fair enough. I was like, it's 100 times more than it should be. No. Okay. Yeah, I mean, I made these slides and I still get problems wrong, so I can relate to that. House Edge and Blackjack. If you're gonna bet $1 million on one hand, is that what happened, or in one evening? How much should the casino expect to earn off of your stupidity? So this, I think, should be positive, right? Because it's from the casino's perspective. So they swapped it around on this problem, so that might be something to note. Now instead of doing the players, we should do the casino. But now you're doing one game, or I guess it doesn't matter how many games. You're just betting $1 million throughout. I think they're trying to show you that every dollar that you spend, you're just going more into the hole. Or you could pretty much plan that. When you go into a casino, like I said, they're keeping their lights on. You know, they're in it to make money. They definitely ain't losing money. They're not just a front for illegal activities. They also do it. They also make money. That was like, what was that, the Rat Pack that performed in Vegas all the time? Did I not get something right? What the heck did I do? It should have been 140, right? Oh, shoot. I missed a zero. Shoot. Should be 140. 14K, is that what it is? I put an extra zero in there. Yeah, okay. Should be 14K. So going back, we want to multiply this by 1 million. We go 3 over, it should be 14. We go 3 more over, it should be 14,000 that they're making. And we're doing it from the casino's perspective, so it should be positive. I put an extra zero in mine. Did not convert that right. Oh man, okay, I think this is the final question. Powerball. So basically we have this Powerball that we're playing on a single $1 ticket. We want to find the expected value of, the winnings for single ticket. The jackpot is 30 million. And then we'll do something stupid. How much can you, if you do 10 a week, how much can you expect to win or lose? But the first thing is you're spending $1. So let's fill that in. Yeah. Adjust this down a little bit. And so we're spending $1 on this ticket. Text. So I believe the first thing on there should be like, you're starting out $1. Basically $1 in the hole, right? And so the jackpot, I believe, is 30 million. And we have a 1 in 292 million chance. We got a prize of $1 million, and it's 1 in 11 million. 50K, and that's 1 in 913,000, so on and so on. I'm not sure why they do this twice. Maybe there's 2 different ways to win $100 is what I would assume. Maybe there's 2 different ways to win $7. If I'm being honest, I don't know. Oh, shoot. No, I can't read that last little one. I think it's 1 in 38. 1 in 38 is what that says. Let me get my annotations up on here. 1 in 38. And so we want to find the expected value of this beast. And I know these aren't pretty numbers, but hopefully you have some sort of calculator or something to do this. It should be doable. Like, I'm going to admit it's not the prettiest thing, right? But it is something you should like kind of understand how to do a little bit. We're going to do 30 million over that thing. 1, 2, 3, 4, 5, 6. But, you know, the moral of the story, I guess, is that in reality, right, we don't always get pretty numbers. Yep. I'm not sure if I broke this one down or not, because I know we did a few examples already with expected value. And so I think I might have just kind of skipped this one with the breakdown. That's a lot of stupid numbers. Okay. Hope this is right. Two decimal places, it's a money amount. Should be negative. You're buying a lottery ticket, you should expect to lose money. This is part of the reason why I didn't walk into a casino for a long time after I studied this stuff. Like, the more games you play, just the more in the hole you can almost bet you're gonna go. It's got a negative value on the game. It's not a good game to play, right? If it's got a positive value, you go for that game. Casinos are smart enough to know this, what expected value is. I'm gonna say old blue, like, was it the Rat Pack that performed in Vegas for the longest time? Sinatra, that was his name. Old Blue Eyes. His daughter said something like she was having a hard time, like, I guess, grasping the fact that he had mafia connections basically, but he wasn't active in it, but like he still dealt with those sorts of people, I guess. And they were not always decent people. Like Vegas is like, I don't know, it's a desert. I think the whole backbone of that city, I think, is pretty much built on nefarious activity and mob connections. That New York is like also has. I've heard you don't build real estate in New York without having mob connections. So if you know anybody that owns real estate in both New York and in Vegas, not gonna name any names, but there's a good connection. There's a good chance they have mob connections. All right, where are we at? This is the last one. We got this problem, and then the next one's like really, really sort of simple. Just a little addition after this, and it's like we got to do one little thing after this. This is the hard part, right? Probably. So I hope it looks like -1 is the first thing you have, and then you have plus, and then you have like what 30 million over here. And this is over that 292 crazy number, 201, 338. Try something out. Like, I don't even care if you get this correct. They are crazy numbers. We do 1 million. We're adding this, we're adding this, summing these things all up. I'm hoping this is what it looks like. Ooh. I mean, if I'm being honest, like, I'm probably going to give you like prettier numbers when I can give you a quiz or a test, right? But like, this should be doable. It's the same concept. You just got to get a little messy with the numbers, but it's the same stuff we've been kind of doing. Where are we at? Is there one person that's going to buzz out? Did they leave? Who's that? Myra, are you still working through this?
Yeah, I'm still working through it.
Okay, fair enough. All right. So I think it should be losing 58 cents. Is what I got when I sum those things up. What are you telling me? What? It should not. You're not making money off of a ticket. We're all getting 81 cents. Should give you minus 58 cents. Okay, so if we're gonna lose what, 58 cents? And we're doing 10 lottery tickets per week for 52 weeks. I think we're doing 520 tickets. How much are we going to expect to lose? An exact amount should be money. Do it 2 decimal places. Is the last thing I'll ask of you today. And you should expect to lose this. I'm not going to say, like, we don't need to explain that. You're buying a lottery ticket. If you're going to go out there and buy a lottery ticket and expect to win money, I don't know what to tell you. Not smart, right? Because it's not a winning thing. They're not in the lottery to lose money. The government's not. So if you're going up there expecting to win money, man. All right. What was it? Minus 301.60, I think is what I'm getting. I'll multiply those two things together. I should be losing $301.60. Yeah. All right. Any questions of anything we've done? Okay.
For the previous one, how did you get the negative negative, what's it called?
Oh shoot. Okay. Yeah. Let me go back. I have that table. Hold on. Let me bring up that table right quick. Seven. Let's see as we're at. All right, so this is the table. So we should start out with a minus $1. We're spending $1. We're guaranteed to do that. The next thing I have is what? 30 million. And I want to add 30 million over 292, 201, 338. And so I'm creating the sum with all these numbers. And let me go back, actually, just do it in, I just do it in Wolfram. I think that might be the best way. So I have a minus $1 that I'm doing. I'm going to add that to, and let me bring up other things down here. There's too many little screens in the way. Okay, so I'm going to shrink this down maybe. Can I shrink it and still see it? No. I'm going to pin this in the corner. That's 31, 2, 3, 4, 5, 6, and we're going over. It is all in my calculator. I can just do that. 292, 201, 292, 201, 338. And I'm adding that to 1 million, which is 1, 2, 3, 4, 5, 6. And I'm dividing that by 1,168,8053 from the table probability. So I maybe am like going maybe a step and just multiplying the value by the probability. But this is my value of 30 million divided by the probability of the 292 million. This is my 1 million, and I'm dividing it by the, what is this, 11 million. And I'm taking the next thing, which is, what was it, 50,000. So there's a 50,000, 1, 50, 1, 2, 3. And there is a 913129 is the probability that I got from the table. There is $100 prize. And there is a 36,525 chance of getting that one. 36,525. Ooh, forgot to divide. There is another $100 prize, and there is a 1 in 14,494 chance of getting that. 494. Forgot my division again. I could win a $7 prize, and there is a 1 in 580 chance of getting that. I could win a $7 prize, and there is a 1 in 701 chance of getting that. I could win a $4 prize, and there's a 1 in 92 chance of getting that. Or I could get a $4 prize, and there is a 1 in 38%, or not percent, 1 in 38 chance of getting it. And so I add these all together. It should be giving me like minus 0.576, rounded up to 0.58.
Okay.
Yeah, and like I said, I combine these, so I guess I could write these separately, right? I could write the 300 million times that. This is my value times my probability. So I did skip maybe a step just by combining my value and my probability into one thing.
Okay, thank you.
But if it's 1 on top on your numerator and you're multiplying by a number, that's coming into your numerator, right? That's like, this is like having a million over 1 times 1 over something. Sorry. We always put things over 1. And so when you're doing like this multiplication right in here, like this part right in here, right? If it's 1 on top and you're multiplying by something that's got 1 on the bottom, I did do that combination, but yeah. But basically it's the value over the probability, right? Value over probability. Yeah, so that is a lot of ugly numbers, if I'm being honest. I will give you probably prettier numbers. But the moral of the story here, I think, is that in reality, we don't always get pretty numbers. So you might have to do it with ugly numbers sometimes. Any other questions? All right, I'm going to stop recording.